Okay, good afternoon everybody and welcome to the colloquium for this week. I'd like to welcome Michael Giudici from the University of Western Australia to talk about automorphism, orders of groups and their master.
Thanks, Aaron. First of all, I'd like to thank the one organiser who is organising this semester. I'm really looking forward to it. It's been great so far. It's a privilege to be here. And for giving me the opportunity to give a talk today. So I want to talk about automorphism groups and what stuff. And so this is joint work with Alex and Cheryl. So, when I was a PhD student, I was taught that every good talk to start with that G is a good every pure seminar should start with let G be a group. So G is a group in this talk, but I always like to have one extra adjective, so that we can apply that group here. And I also have my group of automorphisms of my group G. Now, usually, if I have some sort of structure and I look at the automorphism group, usually I like my automorphism group to act transitively on all the elements of my structure. Okay, which is perhaps not very interesting for a group because, of course, if all G acts transitively on G, well, any automorphism fixes the identity, so I just my identity group. So it's not really much, isn't very interesting. I suppose we could move one step up, and we should have if alt G is transitive on everything in G except all identity. Okay, well then now we can say a little bit more. Okay, well, automorphisms preserve orders. Okay, so every non-trivial element must have the same order. So it must have order P. Therefore my group's a P group. My Cauchy is finite, so it has a non-trivial center. Any automorphism preserves the center. So the center must be the whole group, so it's abelian, everything's order P, so G is cyclic. G is elementary abelian at the same time. So if we have a small number of orbits by the automorphism group, then it's fairly, well, not very interesting. Okay, so let's say omega G be the number of orbits of the automorphism group, group G. And so if omega G is 1, we have a trivial group. If it's 2, we're elementary abelian. So well, we can if we want to, suppose, keep working our way up that chain. And in 1986, so Laffey and Mikhail, 1986, showed that if there was orbits, then either G is the alternating group on 5 letters, or the order G is PVA, PGB. What's this prime pattern? Right, so P and Q are primes. And I give a lot, in this case, that's a soluble group, by Bernstein's PVA and QB theorem, and I give a lot of structural values essentially to determine what the groups are in that case there. For P groups with 3 automorphism orbits, that's still.
So is that right? Surely for A5 it's 4.
Yes. Sorry, I've done the wrong one. Sorry, I've got the wrong result. Thank you. Why did I write down A5? Good question. Because I merged that with the result for omega is 4. Sorry. We'll get rid of that. It's 4. Yes. 2, 3, and 4. Yes, I'm the identity. Thank you. Right. Okay, so, right. Okay, so omega G is that. Okay. So, but instead of going on to omega G being 4, then instead I want to have a result which is on slightly on a different line. Okay, and so this is a recent result of Alex from 2019. And then if the automorphism group has a large orbit, where large is as an orbit with length at least 18/19 of the order G, then G is solved. Okay, so if your group has a very large orbit compared to the order of the group, then you must have a solid orbit. Now, this is actually not sharp, so I suppose Alex thinks that the best bound actually the correct. So your conjectures would actually 3/7 of the order G should be the correct. And that's meant for L2, L28. So that's if you have a large orbit. Now, as we saw in these early results, what really prevents you from having a small number of orbits is the orders of your elements. Because automorphisms are orders. So Zhang, Zhang, 92. Okay, he calls the group an AT group. The group G is an AT group with for every integer k, the automorphism group acts transitively on the set of elements for k. And that, I suppose, is the best you can hope for a group of automorphisms. And so he proved a few results. He gave a very detailed structure theorem, which I don't want to list down here. And also showed that simple groups is meant to be a theme of this semester, so I'll say the only simple ones are essentially some small ones. So A5, L27, L28, A6, and L3. So they're very simple AT groups, where two elements of the same order are always conjugate under automorphism. So let's let O of G be the number of elements, or sorry, the number of element orders in that group. Okay, and so for an AT group, that's precisely when O of G is equal to omega of G. An AT group is a group where the number of element orders is equal to the number of orders. Now, the question then becomes, well, you know, how much can you, or how close does omega of G differ to O of G? Right? Can you say anything if they're close? So, what do we mean by close? There's two quantities we want to investigate. So, not quite enough room here to squeeze it in. Okay. So, so we can look at the difference, right? So the number of automorphism orbits, one is the number of element orders. Okay, so this is always at least 0. Okay. Or we could look at the quotient, which is the number of automorphism orbits divided by the number of orders. And this, of course, is always at least 1. And we can look to see what can we say? How large can this difference be? Or can you bound the difference? And we get it similarly for the quotient. Now, one other quantity which actually is useful to look at is what we call M of G. And this is just the maximum over all A of the number of fields okay. So essentially it's the most that element orders can split up on the automorphism. So there are three main quantities. So these are the two main ones we want to investigate. But it turns out this is quite useful. Right, so, well, first of all, why is this one useful? Well, of course, Q of G. Well, the number of automorphism orbits is at most the maximum you can have for a given order times the number of different orders. And then if I divide by energy. So my quotient, of course, is bounded by the maximum. So that is useful. And equally, I suppose we also have that. Can you still see if I write that here? Yep. So we also have that M of G will be 1. So that means they never split. That's if and only if the difference is 0, which is if and only if quotient is 1, which is of course if and only if G is negative. So we're trying to study these things. So we had two main theorems. Well, the first main theorem tells us that there exists monotonically increasing functions of 1 and of 2. Such that, first of all, I just want I have my G, and I'll take the index of the radical. So that's the soluble radical. So this is at most a function of the difference. And 2, there's another function of 2. So again, this is at most a function, well, we couldn't quite do just a function as a quotient. But we've also got to get the number of element orders in the radical. And so this is where G is the largest solvable solution. So, I suppose if you think of the index of a radical as being like how close your group is to being soluble, then you can bound how close your group is to being soluble. Well, it's bounded by the difference between the automorphism orbits and the orders of elements, and also the quotient. Except when we want to look at the quotient, we can't get rid of also needing to know how many element orders you have in the radical. Okay? So O of radical G, that's the number of element orders in the radical of G. Also, when I say monotonically increasing, that's fine for F1. F2 goes a function of two variables. I mean, monotonically increasing in each variable. So that's our main theorem. So I want to talk today about how we do one, because one reduces nicely to the simple group case. So we can do a lot of analysis in the simple group case. Two, you can reduce to just, of course, in both cases you reduce to just looking at a case where the radical is trivial, but there's much more work involved in the second one. We've got to do a lot of analysis of nice cosets in the socle of the radical and pairing them up nicely so that the quotient is well behaved and all that sort of technical analysis. But I want to focus down on one, which is much nicer in some sense. And we'll see why the monster plays such an important role. So, okay, so let's start off with a nice number. So, if I have a characteristic subgroup, of my group G, then first of all, the difference to n is the most the difference to G. The maximum splitting number for n is the most maximum splitting number for G. And maximum splitting number for the quotient is the most two times difference plus the difference. And so this allows us then to look, okay, we're trying to bound D of G. And so by this one here, okay, if I can look at bounding this number, then I'll be able to bound, if I can bound the order G of n by this, then I can bound the order by D of G by difference. So to prove this, I suppose, well, n is a characteristic subgroup. Okay, and so then the ought and orbits is just unions orbits, okay, because then the automorphism of G must fix n, and so it reduces the automorphism of n. Okay, and so that allows us to prove 1 and 2 quite easily, but then 3 requires a lot more work. But we saw I just adapted the methods. Zhang in his paper for AT groups had also a way of trying to look at AT groups, look at a normal subgroup. And for an AT group, the characteristic subgroup also had to be an AT group, and so did the quotient, and plus some extra properties. So using his arguments and pairing up, we're able to get this nice power. So that's what we have for a characteristic subgroup. So how does that help us? Well, if I take my group G, okay, then so if I take n to be the radical of G, and I take H to G mod n, then, okay, so since H then has trivial soluble normal subgroup, its socle looks like T1 to N1 cross TK to K, and Ti is an ordinary simple group. So know the structure of G1N quite well. Now, we can then have another useful lemma. Well, we know from our first lemma that LH is greater or equal to m of its socle, so T1 to N1 plus TK to NK. So that's our lemma distance. Okay. And then we can then show that this is at least the product from I equals 1 to k of ni times the maximum splitting number for Ti. And this then is then greater than maximum over I, and Ti. So So really what we're doing here is not very hard, but it's just the main observation that, well, if I take some element T in my simple group, okay, say I want O, and if I look in T to the K, then I take T in the first coordinate and whatever else, that's one element of order K. That's another element of order K. I mean of order O, sorry. And so there's K different elements of order O, and you can't map no automorphism of T to the K maps this to that, okay? And these lie in different T to the K forms. As the automorphism group of the direct product of isomorphic simple groups, this is just ought to retest. So if you take the order which gives you the maximum splitting number for this T1, and the order which gives you the maximum splitting number for T2, and so on, then you take the LCM of all those orders, and then you'll get at least this many orbits, automorphism orbits on elements of that order. Because that's how we have it. So that's good. So one thing we have now is that, well, this here, this was bounded by, by some function of difference. Okay? And so Ni is bounded by a function of the difference. Right? So Ni is bounded by function of the difference. Also, the maximum splitting number, that's greater than or equal to Q. And so with Ti also bounded by a function of the distance, of the difference. So that's good. Now, we also have for H, well, I can embed that inside the automorphism group of its socle, because H has no soluble normal subgroups, so there's nothing centralizing the socle. And so this is just, well, we know what this group is. This is sort T1, let's watch a group on N1. Now, okay, so if I look at this order here, so I'm trying to bound the order H. Right? And, well, the Ni is bounded by some function of difference. Okay? And I also know that, well, for a simple group, the automorphism group is small, right? It's well known these are small for simple groups. Like it's the most log to the base 2 of the order of T, but you can probably do much better, but it's at least that. In many cases, it's much, much better. Okay, so that's a pull down, but that's usually sufficient. Okay, so therefore, the order of this group here, okay, it's controlled N1. All we have to do is control the order of the TIs, right? If I can control the order of the TIs, I'm going to bound the order of H. Okay, so we want bound the order of T by some function. So I can bound that, then I'll go bound. And I've got the order of T bounded by a function of Q, the Q is bounded by a function of D, so that's good. n is bounded by a function of d, and so the order of h will be bounded by a function of d. So that's what we want to do, right? So we want to look at these quotients as simple groups. Okay? So I want to study for a simple group, then q of t, it's gone off the board. So q of t. The quotient of the number of automorphism orbits by the number of automorphisms. That's what we're going to do. So we just need to look at that for simple groups. So what we do is we introduce a couple of new functions. Start with a Praeger, my simple group. And this will just be log omega t divided by log of the order. Okay, so that's my Praeger. And we'll do the same for q. Okay, but I can't just take q of t, because q of t can be 1. We'll take log of 1, I get 0, and I'll take log of that. So we're in trouble, so we'll add 3. Yeah, and we'll go log of t. But 3 is, okay, it may look like I'm just creating 3, but there is a reason for my madness. So if the number is at least 1. Okay, so if 1 plus 3 then gets me, everything will then be fine at the top. Okay. But also 3 is the largest number I can do, because I'll always have the q of t plus 3. Okay, this is always best way to omega t over t. Okay. And as Rob rightly pointed out at the start, because if t is a5, I'll get 1 here plus 3, which is 4, which is the number of automorphism orbits. And so that's where you only have, that's where this is the worst case. It's the closest. You get equality then, and in general we'll have that. So that's why we take 3 to this, right? Because 3 is the largest constant we can add, so that this holds. Okay, so they're my 2 quantities we want. And if I can bound this one, then I can bound q of the order of t in terms of q of t. So then, next theorem. Okay, so as we all know, if I have a finite simple group, it's either sporadic, which we don't really need to worry about if we're just worried about asymptotics, or you have the alternating group, or we have the group Lie type. So first of all, if I look at these quantities for the alternating group, then this goes to half as n goes to infinite. And similarly, EQ goes to a half as n goes to infinity. And in fact, actually, you'll get that this is always greater than A5, and epsilon q and n is always greater than epsilon q and n. So I suppose nice thing or feature of that adding 3 is that in some sense the really small groups don't give you really small values of EQ, because by adding 3 you sort of like boost them up a little bit. Okay. And so that's what's happening there. Okay, so for the alternating groups, we have these things, which is good. And then in general, you're going to see some of these actually are quite good, the ANs, because we have the limit as the order of our simple group goes to infinity of epsilon negative 2 is half. And this is also that's good. So we can then get bounds for our order of 2 in terms of but we can say also a bit more. I'll say also how we get those bounds shortly. Okay. But we can do a bit more work. Okay. So we also get that this log of another order by log of t. This will go to 0. And the size of my simple group goes to 30. So your number of automorphism orbits really grows much more than the number of element orders that you have. Also, your ratio will go to infinity as the order of t goes to 30. That's quite good. And part 5. Well, okay, for our original motivation, we just needed asymptotics, but we tried to actually give proper lower bounds to these quantities. And this is always at most log 4 or log 60 with quality if and only if my simple group is A5 and my Q is always at least long size 2 long 413 170 divided by log of the order of the monster. With the quality. These are some damage. So, because we all know, like, the monster has a very small number of conjugacy classes and automorphism orbits compared to its order, right? So, the number of automorphism orbits are just 194. But actually, this is like I suppose, an actual way of actually quantifying why that's the case. So, let's say perhaps to emphasize this. So, as I mentioned, because we're doing this plus 3, the small things like A5, right, there's this very small number of orbits, they sort of like get pushed out in some sense, they're too small. And so the very small groups don't become an issue, and they get hidden. But perhaps to compare the Q value for the monster, right? So Q value for the monster, this is 194.73. But if I look at, say, some comparable simple groups of comparable orders, then if I look at, say, Q of the alternating group, 142 points, and this is roughly 56. Okay, so we're already much bigger. And if I look at Q of L7 13, well, it's at least 6,100. So those two values are much larger than what you're getting from the monster, which has comparable order. So, okay. So that's I suppose it's the reason why we pushed on to get actual proper lower bounds on epsilon Q than what we're originally after. Right? What we're originally after, we didn't need what the lower bound actually was, but we calculated it for the Spranics and saw wants to have the smallest one of all the Spranics, and thought, well, we should see if it can be beaten by anything else. So we did all the hard work to get it out again. So let's say a little bit then about how we go about these things. So, okay, well, for asymptotics, we don't worry about the Spranics. The calculating, so when you kiddie, you just look in the details in the atlas to show that they're always bigger than what you get for A5 in the Boston. So, suppose look at AM. Okay. And so really, right, so we're looking at Q of T is only equal to T, right, number of Automorphism orbits, divided by the number of orbits. Now, well, for the alternating groups, this really comes down to partitions, right, number of partitions. Okay, so, well, the number of Automorphism orbits in the symmetric group is the number of partitions. So anyway, so we've got this. So to get asymptotics, you need asymptotics on the partitions then, which goes back, I suppose, to my motion. And for O of T, right, well then, well, there's whole classical results of Erdős to run about the number of orders of elements in SM. Which then gives you a up or down on the number of order of elements from A. Okay? And so those results are enough to get our asymptotic results for A. And then to work out what value then you need to check to make sure that you get the inequalities there. So next, let's look T to be a group of V type. And let's suppose that, we'll say V rank D. Then, well, again, so I want omega of T, one of Automorphism orbits. Well, of course, this is always a very poor bound. You just take the number of conjugacy classes that your group has. This is the number of conjugacy classes. These may be fused under as automorphisms. So that's a full bound on the number of automorphism orbits. Now, for a simple group of Lie type, as a result of Fullman dynamic, it says that the number of conjugacy classes, not in the simple group, but in the diagonal group, the T is at least q bit. Yep, okay. And so that's the number of conjugacy classes in a diagonal group. You divide out by a suitable number to get you a lower bound in the number of conjugacy classes in a simple group. And then you divide out by the group absolute to get you a suitable. It will give you a lower bound on omega. So that's for that. Element orders. Okay, now we want to. That's a lower bound for omega of T. I'm trying to get a lower bound for this, so I need an upper bound for O of T. Here's a very crude upper bound. Number of orders of unipotent elements. Times the number of orders of semi-simple elements. Right? Any group, any element can be written as a product of unipotent element and semi-simple element, which commute, and so their orders is just LCM. And so that's a very crude upper bound. Now, if I want to know there, well, that's the number of orders that you can have for a univariate element. That's very well controlled by the rank. Right, this is the most, so let's call this number U. Let's call this one S. And of course, so we know U is at most 1 plus upper bound of base P with the characteristic P of the space of Coxeter number. Yes. Okay, so yes, that's due to testing. If not before. Okay, so that's for U. So that's good. For upper bound, the orders of semi-simple elements, with perhaps even an even poorer bound. Okay, is that well S is the most well every semi-simple element lies in a maximal torus. Okay? So if I just take a number of convolution classes of maximal tori times the maximal number of orders in such a tori, well, that's going to be a very poor upper bound of the number of element orders. Okay. I take the largest possible number of element orders in a maximal tori, take the total number of maximal tori, take the product together, that gives you a very poor upper bound. Now, then, okay, for groups of the type, this is well known. For a maximal order for a tori, well, if I have a tori, we do have bounds on their orders in general. Let's call this number A, let's call this number B. So, you know that the order of a torus is the most Q plus 1 to the D. Well, once you know the order of the group, the element orders have to divide the order of the group. Okay? So a very poor upper bound on the number of element orders is just the number of divisors of the number. And so therefore my B will be at most, well, whatever the maximum is of the number of divisors of 1, the number of divisors of 2, the number of divisors of Q plus 1. But you know this is the most, course that's 2, 3 plus 1. 0, 2. So the greatest number of divisors you can have. So your torus is has orders one of these numbers up to Q plus 1 to the D. The number of divisors of such a number is at most this. So that gives you an upper bound B. We know A, and that gives you an upper bound S. Right. So what do we get then? Using those bounds, is we get the order P is the most Q to the half plus psi 2 times T. If the maximum of P and Q is greater than equal to some function of epsilon. So that's using, as you see, there's like a huge amount of wastage in my upper bounds. But those upper bounds are sufficient to get us the asymptotics that we wanted. Okay? And so that works. To get these though, we do need to do a lot more work. In some sense, okay, these upper bounds would work as long as D is large enough. I think I didn't write down how large was large enough, but I think for all Q, I think it was about the order of 1,000. I think they were large enough. But then the smaller values of D, well, there's many rooms of improvement. Okay, so for example, there's lots of repetition of orders in here. Okay, so if I actually look at the actual structure of the tori, we can say much more and get much better lower bounds here. Okay? Equally, once we get down to families of low rank, we can also get much better bounds in general on the number of conjugacy classes. Okay? And so by doing a lot more work, we can just get lower bounds to give us better bounds. Right? By looking at the exact structure of the tori, or better bounds on the number of conjugacy classes. That's what we do. And then again, we get down to, I think we left with 68 groups. Where we just either calculate the Q value explicitly, or again, you do some more work by looking at getting even better bounds on the number of conjugacy classes and things like that. That's a basis of Thank you.
Thank you, Michael. Comments or questions?
Maybe it's obvious, but why did you, in the definition of your epsilon n's and epsilon q's, go for log logs rather than some other shape or
Why are we going for log logs? Well, they worked, they were nice.
Is there any kind of, like, it's rare one has to go as far as log
Log logs. Yeah, I think it's to get the nice half bound coming out for the old data, which I think we do log logs. That's why I took them.
So I would guess that Fulman Geromic is done with algebraic groups. Can you just look at dimensions of varieties and have an infinite analog?
Well, in terms of getting up of
Getting this bound that
getting
you're
bound.
trying to look at, can you make an infinite analog for algebraic groups is the real question.
is the number of automorphism orbits finite?
The dimension of the variety.
All right, give the dimension of variety. No, I'm not sure. But yeah, potentially lots of.
things like tasky monsters would be horrible.
Yeah, we worried also.
Algebraic
Right.
groups, yeah.
Yes. Okay, and then instead of taking the number of, so the dimension of variety.
Are there further questions? Richard?
Years ago, I was trying to work out whether the number of conjugacy classes divided by the log of the group order for non-trivial groups as a maximum, and I concluded that it was M22.
So you want, the number of.
The number of conjugacy classes in a finite non-trivial group.
Yep.
Divided by the log of the order of the group.
Right.
That's basically how non-Abelian it is.
And so it has a maximum of M22.
M22 is the biggest I could find, and I was wondering whether there's technology around now to prove
Right, but
that
that
is in
is.
fact the case.
Yeah, well, perhaps.
Just a little comment.
Yeah, right, yes. Yeah, perhaps.
You don't need a log on the top as well. Otherwise, if we're in a bigger group, that's T over log T.
Very simple.
I got the inequality the wrong way around, right?
That's right.
That's even better.
That seems more possible.
Any further projects for people?
For the whole semester.
Please join me in thanking Michael for his very much.